Okay, so last time I left you, we just finished. What were we doing? We were doing wave basics. I
We
can't
finished
remember.
the oscilloscope.
Oscilloscope, that's correct. We were talking about the oscilloscope. And then I gave you a couple of questions on that. And then I must still upload the mark scheme. So I'll do that today and I'll let you know. But if you have any oscilloscope questions, you can ask me now quickly. I will upload the mark scheme this afternoon. So I'll put that up. Cool. So if you have any questions, you can ask now. Otherwise, we'll wait till later. Okay, so I just want to quickly take you through sound waves. Sound waves can be a little bit confusing, but before we do sound waves, we've got to think about longitudinal waves. And the idea with the longitudinal waves is that the particles don't vibrate up and down if the wave is moving left and right. So you'll see here in this case, the direction of the vibration is in exactly the same direction as the direction of the wave. And that's as opposed to a transverse wave, where the particles are vibrating up and down and the wave is moving in that direction. So like the kind of waves we saw earlier with the string on the rope, that would have been a transverse wave. Also longitudinal waves, the coils or the particles or whatever's vibrating vibrate in the same direction as the wave. And then they say that you'll see sound waves are a good example of longitudinal waves. So sound. Okay, so very important whenever you think of a sound wave, you have to think of a vibrating source. Sound doesn't just come from nowhere. So whenever you hear something, it means that something somewhere is vibrating. So the reason you're hearing me now is because the speakers in your device or the speakers in your earphones are vibrating. And the reason my voice is being transmitted into the microphone on my side is because my voice box is vibrating. So whatever sounds you're hearing at the moment, anywhere, it doesn't matter what they're coming from, that source is vibrating. Cool. And then obviously the vibrations from whatever's vibrating are carried towards your ear, and your eardrum vibrates, and that's how you hear sound. Cool. But what we need to look at is the nature of the longitudinal wave. In other words, what does the wave look like when we think about what a sound wave is? So there's a little highlighted thing over here. I'm going to highlight it for you. It's here at the bottom. You can't really see it so well, but it says there's a to and fro motion of air molecules. And can you see that it's an arrow that's pointing left and right? So we're gonna pick on one of these little guys here. We're gonna find someone in the crowd. Let's focus on this little guy over here. Sorry, let's put him in red. That guy over there. So if we focus just on that little guy over there, that particle is not stationary. That particle is not just sitting in place. What that particle is actually doing is it's moving to the left, then it's moving back again, then it's moving to the right, and then it's moving back again. So it's basically doing a pendulum motion. It's actually going left, center, right, center, left, center, right. So it's literally just going back and forth and back and forth. But it's very important to know that it's not actually moving from that position to a new position. So it stays in that position. It's not moving with the wave. So that particle stays put. It's not moving in the direction of the wave. It's just vibrating in its position left and right, left and right, left and right. Well, and that's what all the particles are doing. So we're singling out one single particle, but that's essentially what every single particle is doing. None of the particles move from the source to the receiver. All they do is vibrate in place. Also, energy, the sound also moves left to right. So remember that these are progressive waves. They're carrying energy. And if you've ever heard a loudspeaker, if you stood next to one, you can actually feel the energy from the speaker. You can feel it almost pushing your body. You can feel it like almost like wind, if I can call it that. Okay, so then when you think about the so-called amplitude and you think about the wavelength and everything of a sound wave, what we do now is we measure, instead of from the top of the amplitude to the top of the amplitude, we measure from the middle of a compression to the middle of a compression. Also, that would be the wavelength over there. But you could also equally measure from the middle of a rarefaction to the middle of a rarefaction, and that would be a wavelength over there. And that's how you measure the wavelength of a sound wave or a transverse wave for that matter. Cool. And that's what they call them, compressions and rarefactions. So compressions are where the air particles are close together, and then rarefactions are where they pulled apart. So compressions are regions of high pressure, and rarefactions are regions of low pressure. And then this alternating compression and rarefaction is what creates the sound wave. Cool. So it's not in the note here, but I'll draw it for you quickly, or you can just imagine it if you want. If you were going to draw a sound wave, it's not a transverse wave, so it's not transverse. I'm just going to write that in the beginning here, just so that we remember that it's not transverse. But what we can do is we can graph it as a transverse wave. And when I say graph it, I mean we can graph a certain property of the wave, and it'll look like a transverse function, but it doesn't make it a transverse wave. So the one property we can graph is pressure. So I'm going to write here P, but I'll write it out just so you can see that's pressure. So measured in pascals. And then this would just be the distance or displacement, something in meters, for example. And then if you look at your wave, what you're basically going to do is you're going to graph regions of high pressure versus low pressure. And then what you're going to end up is you're going to end up with a wave that looks like this. And you're going to think it's transverse, but it's not. So you can think of these regions as high pressure regions, and you can think of these as low pressure regions. And then the baseline is actually not zero. This is not the zero baseline. This is atmospheric pressure. So this is the normal atmospheric pressure that you would experience if the sound wave wasn't there. So when you look at your sound wave, when you go back over here, you can see that this portion here is higher than atmospheric pressure, and this little portion over here is lower than atmospheric pressure. But atmospheric pressure is the line that's straight down the middle over there. Sorry, I didn't realize this is actually in the notes. So yes, that is there. So you can go have a look at that. Cool. Any questions? Does anyone have anything they want to ask or add or contribute, or are you okay with that?
Yes, sir.
You good? Cool. So it's a longitudinal wave. The particles are moving in the same direction as the wave. Just remember that the particles themselves are not moving. They're just vibrating in a fixed position. So they're literally standing still, but they're going a little bit to the left, a little bit to the right, a little bit to the left, a little bit to the right. And then if you think about what a normal wave would look like, it's exactly the same case that the wave starts somewhere where the vibration is, but because every single particle carries that same vibration, you can actually move the energy. So if you just focus, for example, just focus on this little green guy over here. So just focus on him or her, just focus on that one over there. And then what we're going to do is we're just going to oscillate this thing over here, but we're going to oscillate it slowly. But will you see that as I start oscillating the wave, that green guy over there hasn't actually started moving yet. So at this point here, if you just keep focusing on that guy over there, that particle there hasn't actually experienced the wave motion yet. So if you think about that.
So it's because it didn't have the energy yet.
Exactly, the energy hasn't arrived at that point, but you can see as the energy moves, as it moves, there we go. Now you can see that guy moving. So if you look at that snapshot over there, that particle starts moving over there. So when you think about a sound wave, it's exactly the same concept. The sound would start at one point. So you would start, let's say, at a vibrating source. You would have your, let's just draw like a tuning fork over here. And the tuning fork would be vibrating left and right. And then all the particles in the immediate vicinity here now are going to start moving left and right, left and right, left and right. And then this particle over here hasn't felt that energy yet. But what you'll see is that it's going to be a cascade of events, is that every single particle is going to have a knock-on effect. And eventually that guy over there is going to receive the energy. And eventually that's going to go there. Cool. And then once the sound is over, the particles just go back to normal. It's not like it's not like as if they carry on vibrating forever. Once the sound wave is gone, just like here, if I just put a pulse of a wave here, if I just pulse the wave, after the pulse is gone, Nothing. Everybody's back to normal again. Also, all the air particles go back to atmospheric pressure. So you can see the similarities. It's exactly the same property in terms of it's still a wave property. It's just the direction of the particles that are vibrating. They're not vibrating up and down anymore. They're vibrating left and right. So these guys are vibrating up and down, but in a sound wave, they're just vibrating left to right. Left to right in the context of the way we've drawn it, obviously. Cool. Any questions so far? Everyone happy?
Yes, sir.
Yep, good. Happy days. Okay, so I want to show you another simulation then. But I don't want you to get confused because I'm going to show you a simulation that is a pendulum, but I don't want you to get fixated on the pendulum. I just want you to think, of the left and right motion. So when I say left and right motion, all I mean is, I'm going to just take a picture of that quickly. All I mean is just focus on this pendulum moving left and this pendulum moving right. And then you can think of this little thing over here. Instead of being a pendulum, you can think of it as the air particle. So you can think of it as the air particle moving left and right. So that's what you want to do. So let's see if we can get this guy in motion. How do we play on this one? Pause. How do you start this one? No. Oh, you actually have to move it yourself. Okay, so let's give it a small swing there. Boom. So it's moving left and right. And you can imagine that as the air particle itself just moving left and right. Remember, this is not the entire air wave or the sound wave or whatever. This is just one individual particle and it's moving left to right. And now we can start thinking about its displacement. We can start thinking about how far left has it moved and how far right has it moved. So we can pause the video. Pause. Doesn't allow me to pause. Oh, there we go. Ooh, we can pause, we can take it to its furthest point over there, and then we can take a video, take a snapshot, and then we can say that's there. And then remember, we have a symbol that we use for amplitude. We can call this one x naught. So this is the amplitude. It's its maximum displacement. Ooh, and then we can go back and we can let it go to its middle displacement. Oopsie. There we go. And that would just be the 0 line. So at this point, it would just be at 0. So it would be at 0 displacement, or S equals 0. And then what we can do is we can actually let it go in the opposite direction. We can keep playing and we can pause it at that direction. But would you agree with me that this point it's equal and opposite to the amplitude in the opposite direction?
Yes, sir.
Yeah, so this is negative x naught. So this is the negative of the amplitude. And can you see that it's basically oscillating between those two fixed points, and it comes back to equilibrium every half a cycle? Also, what do you think the graph would look like if you thought about it in terms of, we're talking about the displacement of just the particles. So we're talking about one single displacement. So one particle moving left and moving right, moving between x naught negative and x naught positive. And then what we're going to do is we're going to draw a graph. Sorry, can you see the green? Everyone good with the green?
Yes, sir.
Yes.
Yeah, good. Happy days. What we're going to do
Yes.
is we're going to plot a graph of displacement. So this is S for displacement in meters. And this is just time. Just basic shape. What sort of shape do you think it's going to form? In terms of, is it going to be
linear?
So you think it's going to be some sort of up-down thing like that?
No, sir, like it's going down.
It's going down, so you want it to go like that?
No, oh, no. Oh,
No.
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 Start from the top,
Sure.
like up,
Yeah,
and then you just go down.
correct. And then does it go?
Yes, like that.
Yeah, like that. That's good. Yeah. And then will it go up again?
It went negative.
And then it's going to go back to 0.
Then it's going to go back up.
Correct. And then it's going to go back to positive. And then it's going to go back
positive.
to negative. And then would you agree with me that it's just going to keep doing that forever and ever and ever? So if you were going to draw it as a graph, that particle's motion in terms of its left and right position is literally just going to keep going up and down forever. So if we go back to the app, and if you watch it for a few seconds, I can't draw on here, unfortunately, but you can basically see it's going from positive x naught to negative x naught and back again. It's constantly oscillating. Sorry, the screen share just stopped. Let me just go back on screen share. No, I can't see it. It should come back now. Just give it a second. Oh, it doesn't show. Okay, guys, give me 2 seconds. The screen share just stopped. There we go. Got it back. Let's see if it just loads now. There we go. Good stuff. Okay. So you should see it going, I can't draw on here, unfortunately, but you can see if I put the ruler there, for example, it's going to negative x naught, and then it's going in that direction to positive x naught. So it's oscillating, in other words, it's basically going backwards and forwards. So if we go back to our diagram, you'll see here that it's oscillating between positive x naught and negative x naught. So you can say that's x naught there, and that's negative x naught there. But remember, this is not a transverse wave. We've just drawn the displacement as a function of time. And when I say that the displacement, what I mean is the displacement of one particle. Also, this is the displacement of a single particle. Also, it's the displacement of, I'm going to write specifically one particle. Also, it's the displacement of one particle. And we can draw the displacement as a function of time. And then very specifically, if you want to see the shape of this graph, the actual shape of the graph, it turns out that it's a perfect sinusoidal graph. So it turns out that it actually does this. That's what it would look like in reality. And we call this simple harmonic motion. You do it in A level if you carry on. But would you agree with me that that's not a transverse wave? You must understand that that's not a transverse wave. That's just that's the displacement of a single particle drawn as a graph over time. Cool, everyone happy with that?
Yes, sir.
Yes, sir.
Yeah, so this is not a transverse wave. Let me write this at the bottom here quickly, just so you make sure this is not a transverse wave. It's a function. When I say function, I mean that in the mathematical sense. It's an equation that says this is what's happening to the displacement of that single particle. Cool. Now, if you think about any speed velocity graph, speed time graph, if you forget about particles for a second, if I give you any velocity displacement time graph, it doesn't matter what it looks like. Let's just say it's a displacement time graph like that. Would you agree with me that there would be a corresponding velocity time graph as well?
Yep.
Yeah, so you would have to be, you not have to be able to, but what I'm saying is you have to realize that if something is moving over time, it means that it has a certain velocity over time as well. So you could map the velocity of this graph, for example, and then you could break it into sections and have a look at what's happening over the section. So you could take that section, that section, that section. Here it has a constant gradient, so therefore it has a constant speed. So you'd have a constant speed over there. This section over here, it's actually not moving because this displacement is not changing. So this graph would come down and it would sort of be on the thing over here. And then over here, it is, it's traveling at a constant speed in the opposite direction. So this one would come down here like that. That's just a basic example. This has nothing to do with waves or particle motion or whatever. I'm just giving you an example that we can look at the displacement graph and we can find the velocity graph. That's all I'm saying. Cool. So we have to be able to do that for the particle as well. So let's go back to the oscillator and have a look. Let's see what it looks like. And we just pause and we play. Now you've got to think about this thing. It has two turning points. And if you think about throwing a ball into the air, what happens to the velocity when it reaches its highest point?
It equals to 0.
It's equal to 0, 100%. I couldn't have said that better myself. So at its highest point, it's equal to 0. So where on this pendulum or where on this oscillator do you think the velocity is equal to 0?
Those two endpoints there.
Those two
like,
endpoints, correct, on the left and on the right. So at those 2 points, it's when it has to turn around, and it's going to be at its highest point. Now, if you think about, I'm going to quickly pause it and then I'll give you an example. Oopsie, I closed it. I must use the pen to do that. If you think now to quickly, if it has potential energy here, and it's going to come down and it's going to get converted into kinetic energy, then it's going to carry on and it's going to get converted back to potential energy. At which point do you think it's going to have the most kinetic energy? At which point do you think it'll have the highest amount of kinetic energy?
Most probably
Center.
In the center,
Center.
correct. Correct. This is where you're going to have the most EK, because all that potential energy has been converted to kinetic energy. And then as it starts going up to the other side again, as it starts moving this way, it's going to lose EK, because all the EK is going to be converted to EP. So it has its most kinetic energy at the bottom point.
So is it also, is it,
yeah.
sorry, is it also the most because the distance is 0, so it's like at the middle one, like the EP would be the distance. It's like it doesn't even have a distance. That's the beginning. So maybe
yes, what you're saying. Yes, it has no potential energy. It only has kinetic energy. I think you can actually put it. Yeah, talk to me.
And remember, it's always 2, like they add up. So
correct. So you can actually see it on this graph here. If you look at what it looks like, you can actually watch the graph on the left, and can you see it gets converted between EK and PE? So you're absolutely correct. So if we pause it, and if we just play, there we go. So it has maximum potential over there. Then we let it play. Let's see if we can stop it in the middle somewhere. There we go. And there it has all the kinetic energy, but 0 potential energy. So I think you're absolutely correct in that sense. So that works nicely. And then what you can do is you can think about this in terms of a velocity time graph. You can say it's going to have, at this point, it's going to have 0 EK. And if it has 0 EK, therefore it has 0, does it have velocity if it has no kinetic energy? I think maybe there's a bit of a delay, but it doesn't matter. So if it has 0 kinetic energy, it also has 0 velocity. So at the point that it has 0 kinetic energy, it also has 0 velocity. So if something is not moving, it does not have kinetic energy. And then when you play it forward, oopsie, let's see if we can get it to pause in the middle there. There we go. At this point over here, it's going to have max EK and therefore max velocity. So it's going to have a maximum velocity in that direction. Cool. And then the other thing that you've got to realize is that it's actually changing direction. So would you agree with me that the velocity is going to change from negative to positive? So the velocity is, it's not always going in the same direction. In one instance, it's going left, so you can call left negative. And then the other instance, it's moving right, so you can call right positive. So the graph of the velocity time graph is also going to be oscillating between positive and negative. Also, you can try and summarize that for yourself, and you can think now that you're going to have a velocity time axis like this. So velocity time, and it's going to be oscillating between maximum, minimum, but maximum and minimum in both directions. And it's going to look exactly the same. You're going to end up with a graph that looks like that. And you can remind yourself that on this graph here, this is max velocity in one direction. So this could be max, I'm just going to write you a positive V. And then you can highlight the bottom point over here, and you can say that that over there is max. Sorry, the iPad now is being a bit funny. Max. No, it's not going. Okay, that's timed out. But you can basically say that's the minimum. That's not the minimum, sorry, the maximum, but in the opposite direction. So you can do that. Let me just quickly see there. I probably need to put the pencil back in, just let it meet the tablet again. And then this would be, nope, still not writing. Oh, there we go, there we go. There we go. So this would be, okay, it's bummed out, it's dead. Okay, but in any case, that would be the maximum negative velocity. And then you would find 2 points on the graph. That would be the 0 velocity point, and those would be the 2 end points. So I'll highlight these in pink. And this is basically when it's at its end point over here. End points, meaning if you look at the oscillation, it's at the end point like that, where the velocity is 0. Also, the velocity is 0 there, and the velocity is 0 there. So 0, max 0. So, yet?
When the particle just moved once, is that correct? Now that
correct,
when the
exactly.
Particle just moved once.
Yes, okay. So that's one complete oscillation. So if you go back to that point that we started at, if you go back to here, that's one complete oscillation. It moves from maximum velocity in one direction to the end point, then it turns around, it accelerates in the opposite direction, it gets to its maximum velocity in the opposite direction, and then it goes back to 0 again, and then it goes back up to the other point.
Mm-hmm.
So that's one complete oscillation for that particle. So
what do we call this graph? Like, do we just say, is this the oscillation of a sound?
Of a sound particle, correct. This is, if you just go back to just regular P3, this is literally just a velocity time graph or a displacement time graph for a single particle. So it is the velocity time graph of a single particle. So you've got to remember that what we're talking about here is literally just, I'll just draw it in another color so you can see. Let's do pink. It's literally just one single particle. It's bummed out again, moving left and right. Yeah, there we go, like that. Between maximum and minimum. So I'll show you quickly, I'll show you what the question looks like, and then you'll understand what I'm saying. So if I show you what the question is, then you'll see regressive waves, oscilloscope, wave basics questions. That's a nice one, that's a nice one. Here's a nice one with a coiled spring. You can go and have a look at this in terms of wavelength and stuff. Frequencies. They love these questions on frequencies of electromagnetic radiation. Not this one, not this one. Here we go, this one over here. So when a sound wave travels in air, the air particles vibrate. A graph of displacement against time for a single air particle is shown. So I just want to highlight here quickly, this is precisely what we've been talking about the entire time. They're telling you that it's a single air particle. So it's the displacement for one single air particle. And then it says which graph best shows the kinetic energy of the air particle as it varies with time. So I won't do this question for you, but I just want to show you that this is what the question looks like. So they'll give you graphs, but they'll be very specific, and they will tell you that it's for a single air particle. So that's very important here. It's for a single air particle. It's not the sound wave. It's not a transverse wave. It's the displacement time graph for a single air particle. And then they ask a question about longitudinal waves. So that's basically what you can expect in terms of a question. Cool, any questions? Otherwise, we're done with that lesson. You good?
No, sir. Okay. The first. Yeah. Okay, never mind. No.
No,
okay,
ask,
but
please, please.
One T, the capital T, was that 0 again?
Let's go back to the question.
Yeah, was it like it said 2 T's and 1 T?
T is period. Remember in in
okay. Yeah.
in wave basics, we use capital T for period. So what they're basically telling you is that, I'll draw it for you in a different color quickly. Let's do it in green. They're basically telling you that's the period of one wave, that's the period of two waves. So they're giving you the period of the wave. And it makes sense because they've drawn exactly one perfect wave inside one period. So there's your one wave in one period.
Oh, so it's just like SIS, but a bit shifted. Okay, sorry. Yeah.
Correct. Yeah. So they've just squashed a little bit. But remember that it's this is not a transverse wave. This is one single tiny particle moving left and that same particle moving right, where we can, let's assume this is negative and assume this is positive. So if this was on the graph, this would be positive and that would be negative. And all we're doing is we're graphing the displacement over time. So we're graphing the displacement of that single particle over time. Cool. If you don't have any questions, then we can end the meeting now. Then in the second lesson, I just want to quickly show you a couple of tips just to help you to memorize the electromagnetic spectrum. Cool, but otherwise, if you go, then we can end this lesson now.
Sir, can you work out this one question, please?
Sure. Is it in the wave basics?
If you, it's on the exact PDF where you are on, but just go down a page.
Oh, down a page. Sure. This one, maybe?
The 2017 November QP13.
Actually, just hold on a second. Just hold it. Yeah, yes. Talk to me. Sorry, yes.
Yeah.
This one.
Question 23.
This one.
Yeah, can you just work that out? Because my answer varies from the mark scheme's answer, so I'm just uncertain. Can you?
Okay, so you've got to find the period. So you've got to find, if you can find one complete wave. It's going to be difficult because the markings don't line up nicely. So what I'm going to do is I'm going to count 3 waves. I'm going to count this as 1, that's 2, and then I'm going to go to this point over here and I'm going to call that 3 waves. Ooh, hang on. I must be careful because of this sidebar here. If I count that as 3 complete waves, I can say that 3 waves, 3t is equal to 0.4 seconds. And then you can work out t for one wave. So you can say that the period for one wave is 0.4 seconds over 3. And then you have frequency is equal to 1 over t.
So I did that, and my answer is A, but the mouse scheme says that the answer is D. That's
so you
why
got 8. I don't actually have a calculator with me, so let me just have a look quickly. I'll just do it on my phone while I'm here. So 0.4 divided by 3, that, and then I need to do 1 over that. 1 divided by answer
7.5.
7.5.
7.5.
Oh, probably my calculator.
Cool, no problem. It's mine also just gave me 0.83333. So I probably did exactly the same thing. Your calculator is doing the BOD mass wrong, so you have to put the brackets in the correct place. So it's doing the order of operations in the wrong order. It's probably dividing before it's supposed to multiply or something.
Okay,
cool. But guys,
thank you, sir.
No problem. Guys, take a 15-minute breather. The next lesson is not going to be that long. So take a 15-minute break, come back at 5 to 9.
Awesome.
We'll see you guys now. Bye.
Bye, sir.